Okay, so let's finish our PowerPoint. We're talking about heat. What is heat? Heat is also called enthalpy. Notice it has a H in it, enthalpy, and that change in enthalpy is known as delta H. Delta means change, which is going to be important. So what is the change in heat? Well, let's see. Heat's thermal energy that flows from something hotter to something colder. And the hotter substance transfers its kinetic energy, or heat, to a colder one. So heat energy is added, the speed of the particles increase, the particles increase speed, the faster the speed, the greater the temperature. Ooh, hello. Okay, so here we have our heat equation. Q equals mc delta T, or Q MCAT, right? Yeah. MCAT. So what does that mean? Q is the heat energy. Oh no, it's an equation. We have to start putting numbers in equations and doing calculations. Sorry. Yeah, a little bit of that, but not too much. Okay, so just a little algebra, that's all. So we got Q, which is heat. Heat is usually measured in joules, could be kilojoules, could be calories. It's just heat energy. Whatever the units are, those are the units, okay? M is the mass of the sample in grams, which is usually G. Could be kilograms, but usually it's in grams. So, and then of course comes the C. What's a C? C is the specific heat. What is the specific heat? That's the amount of heat, your vocabulary sheet that you did already. The specific heat is the amount of energy it takes for something to raise its temperature in 1 degrees. So, look at what the units are. Joules, which is energy, per gram per degree C. So 1 degree C, 1 gram, and how much energy that is, that's in joules. Okay. Then we have the delta T. There's another delta again. What's the little triangle? Delta T, which is a change in temperature. Temperature, not gas laws anymore. It's just Celsius. Do it nice and easy. So all we need to do is figure out what the change in temperature is. What's the change in temperature? It's the final temperature minus the initial temperature, or the change. But Mr. G, what if I do it the other way around? What if I have a negative number? Well, that's heat in versus heat out. Don't worry about that, okay? Save that for college. So, here's a practice example of the equation. So how many joules of heat are needed to raise the temperature of 25 grams of water, 10 degrees C to 60 degrees C? So let's see. It's always good to write out the things. I'll give you 1 or 2 problems to practice on. It's really easy. Okay, so we got Q equals mc delta T. That is our equation. So what are our variables? Q is heat. That's what we want to know. M is mass. Here it is, right from the sentence. What's the C? The heat capacity of water. Somebody's got to give that to you. Obviously, table B got it for you. The units are 4.18 joules per grams per degree C. Mr. G, do I have to memorize that? Of course not. I'm going to give you the heat capacity. Now, this, of course, is the heat capacity of water. It could be the heat capacity of something else. So I'll give you some practice questions on those. And then we have our delta T, which is the change in temperature, the final minus the initial. So final is 60, initial is 10. So 60 minus 10, the difference is 50 degrees. 50 degrees Celsius. So now, all we do is we plug and push the buttons in our calculator. Lucky for us, we're solving for Q. So all we do is we type in the M, C, and the delta T. What's the M? The M is 25 grams. What's the C? I gave it to you. It's 4.18 joules per grams degree C. What's the temperature? It's 50 funky looking degrees C. And notice the units are going to cancel. Degree C, cancel. G's, cancel. We are left with J's. So we push the buttons in the calculator. We end up with 5,225 J's. Now, if they asked you, which I'm not going to, but maybe somebody will. If they ask you what it is in kilojoules, a kilo is a 1,000th, and my 6th grader just learned that, so hopefully you guys know that. So we're just moving the decimal place 3 times. So it's 5,000 joules, which is really 5.222225 kilojoules. But just follow the units, have them cancel. I'm not going to be mean to you. Okay. We know the first law of thermodynamics. Here comes the second law of thermodynamics. The second law of thermodynamics says, now this of course is the long way of saying it. It is the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. Mr. G, do I have to memorize that? No. What does that mean in English? It means the entropy of an isolated system never decreases. What is it? What does that mean? I don't know, Mr. G. Such systems spontaneously evolve towards thermodynamic equilibrium. Oh, Mr. G, more words, more words. What is that saying? The state with maximum entropy. What does all that mean, Mr. G? Oh, well, let's see. Entropy is the amount of disorder in a system, which hopefully you did in your vocab. Okay, so entropy, the symbol for entropy is S. Why? I don't know. So entropy is S. Enthalpy is H. Mr. G, am I going to have to learn all these things with the delta S and the delta H and then a delta G, which is Gibbs free energy? No, you'll learn that in college. Don't worry about that for now. Okay, but the idea is that it's disorder of a system. And what do you mean by a system? Well, this is my personal favorite. Answer is greater disorder means greater entropy. So, why is your room messy? Entropy. What do you mean? That is the second law of thermodynamics. Your room will get messy, just the way it is. And what does that have to do with anything else going on around here? Well, once again, entropy has to do with disorder. The world, according to the second law of thermodynamics, the world is going spontaneously into a mess. Entropy will always be increasing. So, your room will continuously get messy. What do you mean, Mr. G? Well, doesn't your room always get messy? Yes, it does, until my mom comes and yells, clean up your room. Well, guess what? When you're cleaning up your room, you are putting energy into the room. The room will not clean itself. If it would, I would be so happy. Because then my room would be cleaned by itself. But I got to put energy in to make it clean. So, the world is going to hell. That's what entropy means. So, here we have cards. You have cards. They're all in order. And then you have the game called 52 Card Pickup, if you've ever played it. And, of course, which one is the bigger mess? Obviously, this is the bigger mess. So this one has the greatest entropy. Will these cards magically go this way? No. But these cards can go this way. But, Mr. G, I can make these cards go in order. You could, but you got to put a lot of time and energy, notice the word energy, into it to make it go that way. But just tossing it in the air, you're going to end up with this. Okay, so entropy means the bigger the mess. And that's the way the universe goes. Okay, especially if you're in Texas. So, we have entropy changes in a system. So, let's talk about a solid versus a liquid. A solid is nice and organized. A liquid, they're just molecules wiggling around. So that means going from a solid to a liquid is increasing entropy. Just like ice will melt on its own. Water does not magically turn to ice unless you put it in the freezer. Oh, yes, we're putting it in the freezer. We're putting energy in because the refrigerator and freezer is plugged in. So energy is going into that system. But Mr. G, in the winter it's going to freeze. It might snow on the weekend. Yeah, that's temperature going down. That's something else. Okay, so next, gases. Notice the molecules flying around. They have more messy than the liquid. So the liquid has less entropy than the gas does. Gas is a bigger mess. The molecules are flying all over the place. How about this case? We have a solid. We dissolve it in a liquid. Now what's happening? The molecules are spreading all over the place and making a big mess. Oh no, that's entropy. Okay, how about this one? If you increase the temperature, you're adding more disorder, which means you're adding more of a mess. So the hotter something gets, there's more entropy, which kind of makes sense because remember, solid to a liquid to a gas is making a bigger mess. Okay, here's another one. Don't worry about this one. If you're confused about the entropy before, this is going to confuse you a little bit more, but don't worry about it too much. Okay, so here's an equation. We got two ammonias. They're breaking up into two nitrogen here and three hydrogens. So obviously, if you remember these types of reactions, this is a decomposition reaction. Okay, so ammonia is decomposing. Okay, so it's going from ammonia to nitrogen and hydrogen. It's going from 2 moles, a 2 in the front, or 2 molecules, to 4 moles, or 4 molecules. So we're going from something that has 2 pieces to something that has 4 pieces. It is breaking up into going from 2 to 4. You're making more pieces. You're breaking the puzzle in pieces. You're breaking the egg. Humpty Dumpty fell off the wall. You're not putting them back together again. So here, ammonia wants to go this way, and ammonia likes to decompose. Why? That is why most decomposition reactions tend to go. Okay, so how do we figure out the change in entropy? What's the entropy delta S? Or just S, think of it as mess. More mess. The more entropy, the more mess. And mess has 2 S's, so that should help you. Mess. So liquid nitrogen evaporates, going from a liquid to a gas. Delta S is increasing. Bigger mess. Liquid wax solidifies. A liquid goes to a solid. That's making decreasing mess. Because if you spilled the wax, it would get all messy, but a solid candle, obviously less messy. So this is a decreasing in entropy. A candle is burning. That's a tough one. But what do you have? You have a chemical, something with carbon and hydrogen, and it's burning. Is it going to go back? No. Is it giving off energy? Yes. Is it going to make a mess? Yes. So bigger mess means entropy is increasing. Salt is dissolving in water. Once again, we had that in the PowerPoint before. You have a solid and you have water. You mix it together to make a solution. You just made a mess. So that is messy. Liquid water is heated. This one's slightly tricky. It's still liquid water, so it's not a phase change. It's not a chemical reaction. It's not burning. It's not breaking up, but what is it doing? The temperature is increasing. So increasing temperature means increasing delta S, increasing entropy. Those molecules are moved a little bit faster. A little bit faster is a little bit messy. And that is the end. Hopefully I didn't confuse you. So what I'll do is I'll give you some little worksheet questions with some calculations, which you can practice the calculations here. Maybe I'll go over some of them with you. So easy stuff with the heat equation. Entropy is a little confusing, but all you need to think about is which is the bigger mess. Bigger mess, bigger S. Got it? Good. So next time your room is a mess, All you need to say is, but it's entropy. That is the second law of thermodynamics. Now, of course, usually parents don't fall for that one, so don't blame me. But it is true.